Good morning. In today's session, I am going to explain you some more problems from the topic work power energy given in previous JEE main. Let us move on to the problems. Read the problem carefully. So, we are going to learn some more problems on work power energy. Already in the previous sessions, we have completed the problems up to 50. So, let us continue with question number 51. A small particle moves to position, so that is the final position, moves to position 5i minus 2j plus k from its initial position 2i plus 3j minus 4k under the action of that given force. Find the value of work done in joules. So, here the displacement vector is final position vector minus initial position. Actually moves to this position. So, this is the final minus initial 5 minus 2. It is 3i minus 2 minus 3 minus 5j plus 5k minus plus 1k minus of minus 4. It is plus 5k. That is the displacement. Final minus initial 3i minus 5j plus 5k, and the force vector is 5i plus 2j plus 7k Newton. Find the value of work done. Work is equal to F bar dot S bar. It is the scalar product of force and displacement. So, here what is the dot product? 15 minus 10 plus 35. So, this is 15 plus 35 is 50, 50 minus 10 is 40. So, the answer is 40 joules. So, that is a numerical problem. So, answer is 40 joules. Move on to the next. A lift of mass 500 kg. So, mass of the lift is given as 500 kg here, is descending with an initial speed 2 meter per second. Its supporting cable begins to slip down to fall with a constant acceleration. So, downward acceleration given to that is 2 meter per second square. The kinetic energy of the lift at the end of fall through a distance of 6 meters. So, when it falls through a distance 6 meters, what is its kinetic energy? So, kinetic energy is half mv square. So, here mass is given, but final velocity, that is velocity at the end of 6 meters is not given straight away. So, you need to find out velocity. See, from this equation, what equation connects them? Yes, v square minus u square is 2as. So, as v square minus u square is 2as, here v square minus u square is 4, that is equal to 2as. So, v square is equal to, if you bring this to the other side, 4 plus 2 2's 4 into 6, it is 24. So, 24 plus 4 v square is 28. So, substituting that v square here, half into mass is 500, v square is 24 plus 4, it is 28. 28. So, it is 14 into 5 is 70. So, 700 or 7000 joules. But here if you look at the options given, it is given in kilojoules. So, here this is 7000 joules is 1 kilojoule. So, the numerical value here is 7. Answer is 7000 joules. If you convert that into kilojoules, it is 7 kilojoules. Go to the next. A 0.4 kg mass. So, mass of the block body given is 0.4 kg, takes 8 seconds to reach the ground when dropped from a certain height p above the surface of earth. Loss of potential energy in the last second. So, here last second is 1/8 second. Last second is 1/8 second. So, loss of potential energy delta PE is equal to mg into delta H. That is the fall in that particular time interval. Fall in the nth second is nothing but S into N. That's it. So, here let us substitute. Here it is mg, Sn is equal to u plus a by 2 into 2n minus 1. Sn is equal to u plus a by 2 into 2n minus 1. In case of freely falling, u is 0, a is g, so g by 2 into 2n minus 1. So, g by 2, Sn place, in place of Sn we are substituting g by 2 into 2n minus 1. Okay. So, let us substitute the values. Mass is given as 0.4 kg, 0.4, g is given as 10 meter per second square, again 10 by 2 is 5, n is given as 8, 2 8s are 16 minus 1, it is 15. So, here 4 5s are 20, so let us simplify that. So, 4 5s, 0.4 into 5 is 2, 2 15s are 30, 30 into 100, it is 300 joules. Answer is 300 joules. See here, 0.4 into 5, it is 2, 2 15s are 30 into 10, so it is 300 joules. That is the answer. So, here the loss of potential energy is mg into the distance through which it falls in that particular second. Distance travelled by a freely falling body in the nth second is g by 2 into 2n minus 1. So, mg into g by 2 of 2n minus 1, that is what we have taken over there. Go to the next problem. A spherical body of mass 2 kg. So, mass of the body is given as 2 kg here, starting from rest, acquires a kinetic energy, that is 1000 joules at the end of 5 seconds. 5 seconds. Force acting on the body. You can do this in so many ways. Fs is equal to lost kinetic energy or gain in kinetic energy. But here the displacement is not given. So, you can find out the displacement from the data given, or we can also use another relation. Force into time of action of force is change in momentum or gain in momentum. But from the relation Ke is equal to p square by 2m, p is equal to square root of 2m Ke. As initial Ke is 0, initial momentum is 0. So, final momentum minus 0, that is the final momentum, becomes Ft. So, Ft is equal to change in momentum, that is 2m Ke. So, if you are sharp enough, if you are very thorough with all the formulae, this will be the straight formulae. The advantage of direct formulae, advantages are two. One is you can save time, the other one is if you go for lengthy calculation method, we may be wrong at some calculation. If you choose a shorter calculation method, there will not be errors in calculation. So, here we are choosing Ft is equal to change in momentum, that is square root of 2m Ke. F we need to find, and the t end of 5th second, at the end of 5 seconds. So, t is 5. This is square root of 2. Mass of the body is given as 2. 2m. Kinetic energy is given as 10,000 joules, that is 10 to the power of 4. So, F into 5, square root of 2 square is 2, square root of 10 power 4 is 10 square, that is 100. So, 5 gets cancelled 20 times here. So, the force acting on it is 40 Newton. So, the numerical value of that for our problem is 40, right. So, force into time of action is, that is the impulse, which is equal to change in momentum or gain in momentum. Look into this problem carefully. An object of mass m initially at rest on a smooth horizontal plane starts moving under the action of force F applied at an angle theta, where theta is related to the displacement. Theta is not a constant factor, it is varying as the block moves. As per the relation, theta is kx, where k is constant, x is the distance covered by the body. The expression for the kinetic energy is given as x by k into sine theta. You need to find the value of x. You see here, a force is applied at an angle theta which varies with the displacement of the block. So, after some distance, the energy acquired by it is given by x by k into sine theta. So, here actually energy acquired by the body is nothing but work done by the force on the body, which is given by F cos theta into ds. F cos theta into ds. The component of this force along this direction is F cos theta into, if its displacement is s, you will be getting that by taking the integral, because theta is a variable function of x here. So, but here from this relation, theta is equal to kx, d theta is equal to k dx, from which dx is equal to d theta by k. Substituting that here in place of ds, dx. So, E is equal to integral f cos theta dx is equal to d theta by k. As f by k is constant, you can take it out of integration. Integral cos theta d theta is sin theta. So, this is the expression we got as per the relation between theta and x here. But the final expression they gave us is E is equal to x by k sin theta. On comparison, x is equal to f, which is given as 2 Newton here. So, the value of x is equal to 2 here. That is the answer. It is quite interesting. So, it looks like a big complicated problem, but it is very simple. So, from the definition, work is the dot product of force and displacement F s cos theta. Here, as s and as theta is varying with s, we have taken it as integral f cos theta ds, where ds is given by d theta by k, and finally we could get the answer. That is the best method for sure for that problem. Go to the next one. A block of mass m moving with kinetic energy E compresses the spring through a distance 25 centimeters when its speed is halved. Here, the most important thing is lost kinetic energy is converted into elastic potential energy of this compressed spring. See here, lost kinetic energy is initial kinetic energy minus final kinetic energy. Here, when its velocity becomes 4, as kinetic energy is half mv square, or as kinetic energy is proportional to v square, when velocity becomes half, kinetic energy becomes 1/4 of its value. So, lost kinetic energy is initial minus final, that is equal to half k x square. E minus E by 4 is 3E by 4, this is half. Now, you need to find out the spring constant of the spring, k x square 25 centimeters, centimeters converted into meters by 100. So, 25 by 100 into 25 by 100. So, here this gets cancelled 4 times, this gets cancelled 4 times. See here, you want to find out the value of k here. So, how do you find out k here? From this, k is equal to 3e by 4, 3e by 4 into 2 into 4 into 4. You are taking this denominator to the numerator if you goes to the other side. if it goes to the other side. So it becomes 2 4s are 8 3s are 24 E. So the spring constant of the spring is 24 E. But here the spring constant of the spring is given as NE. You are supposed to find the numerical value small n here. On just comparison, K is given as NE. So in place of N, we got 24 here. So the answer for that problem is the value of N here is 24. Okay. Lost kinetic energy is equal to the gain in potential energy when the spring is compressed. See, you see the next problem, exactly similar model with changes in the numericals. Look here, a 0.5 kg block. Mass of the block is given as 0.5 kg, moving at a speed of 12 meter per second. Initial velocity is given as 12 meter per second. Compresses a spring through a distance 30 centimeters. If you convert that into meters, 30 by 100, when its speed is halved. So the final speed is halved. 12 by 2, it is 6 meter per second. What is the spring constant? Just now we have done a problem of the same type. So lost kinetic energy is gain in potential energy of the spring. So half m lost kinetic energy. This is half m u square minus v square is equal to half k x square. Actually, you can cancel that half on both sides. Mass is given as 0.5, u square is 12 square, v square is 6 square. This is half, x square is 30 into 30 by 100. Look here, 30 into 30 by 100 into 100. Actually, 2 zeros get cancelled. Half k x square. We need to find out k here. So this is 0.5 into 12 square is 144 minus 36. That is, actually we have cancelled that half on either side, isn't it? So it is just k x square. Okay, k x square is 30 by 100 into 30 by 100. So this is k times 9 by 100. So k is equal to 0.5 into 144 minus 36 is 108 into, if you take this to the other side, 100 by 9. 9 gets cancelled 12 times. 12.5s are 6. So k is equal to 600 Newton per meter. So the spring constant of that spring is 600 Newton per meter. So lost kinetic energy is half k x square. So here half gets cancelled. M into u square minus v square is k into x square. X is given as 30 centimeters or converted into meters. Right? Now look here. A block moving horizontally on a surface with a speed 40 meter per second splits into two parts, two equal parts. One of the part moves with 60 meter per second in the same direction. Then fractional change in kinetic energy. Let's try to understand the problem. A block splits into two equal pieces. One piece moves with some velocity in the same direction. What is the fractional change in kinetic energy? First of all, fractional change in Ke is equal to final Ke of the system minus initial Ke of the system divided by initial Ke of the system, or this is final Ke by initial Ke minus 1. That is the fractional change in kinetic energy. Fractional change in kinetic energy is change by initial. Change is final minus initial. By initial becomes fractional. So, final Ke by initial Ke minus 1, that is the fractional change. So, here you need to follow this problem carefully. Let us take the initial mass as m. It splits into two equal pieces of masses m by 2. The other piece mass is also m by 2. And velocity of the first piece, that is u, is given as 40 meter per second. Okay, that is the original velocity of the body is given as 40. First piece moves with a velocity 60 meter per second in the same direction. Right? So, we need to find out velocity of the second piece also, only then you can find out the final kinetic energy. So, look here, by applying law of conservation of momentum, when an object suddenly splits into two pieces, there is no external force acting on the system. Total momentum before splitting is equal to total momentum after splitting. So, here mu is equal to m1 v1 plus m2 v2. So, let us substitute the data here. It is u is 40, m1 is m by 2, v1 is 60 plus m2 is m by 2 v2. Throughout you can take m as common factor and cancel. This becomes 30. So, v2 by 2, look here, v2 by 2 is equal to 40 minus 30, that is 10, implies v2 is equal to 20 meter per second. So, v2 is equal to 20 meter per second. So, this is the data now. Problem is very simple if you come to this step. Look here. So, fractional change is final kinetic energy by initial kinetic energy minus 1. So, here first let us try to find out initial kinetic energy, that is half m into u square, that is 40 square. So, half m into 1600, that is initial Ke. Okay, Ke1. Final Ke, let us take it as Ke2, that is half m1 v1 square plus m2 v2 square. Because masses of both pieces are common here, m by 2, I am taking it as outside. So, half m by 2, v1 square is 60 square and v2 square is 20 square. So, here this is half m by 2, 3600 plus 400. So, that is 4000, 4000 by 2, it is 2000. So, m by 2 into 2000. What is the fractional change in Ke? Final by initial minus 1. So, fractional change in Ke is final by initial minus 1. So, final is m by 2 into 2000. Initial is this one, m by 2 into 1600, m by 2 into 1600, right. So, here m by 2 gets cancelled, it becomes 20 by 16 or it is 5 by 4. It is 5 by 4, right. So, here it is x is to 4. So, very obviously the value of x here is 5. So, this is not 5, that is not the right answer. See here, I did not complete the problem yet. See 5 by 4 minus 1, isn't it? KE2 by KE1 minus 1 is the answer. Minus 1. This is 1 by 4. But here it is given that, look into the problem, it is x is to 4. It is given as x is to 4. So, fractional change in KE is given as x is to 4. X is to 4. Okay, but we got it as 1 is to 4. On comparison, the value of x is equal to 1. That is the right answer. What is the fractional change in KE? That is final by initial minus 1. So, 5 by 4 minus 1, 1 by 4. So, the in place of x we got the number as 1. So, that is a numerical question with correct option as 1 here. Go to the next problem. It's interesting problem. Look here. In a spring gun having spring constant of the spring is given as 100 Newton per meter. I am just note down the data. A ball of mass 100 grams. If you convert that into kg, 0.1 kg is put in the barrel. The spring is compressed through a distance 0.05 meters. It reaches the ground at some point. What is the distance at which it strikes the ground? See here, it is at a height 2 meters above the ground. Find the value of d. It is very important to understand the problem. If you really understand the problem, it's a simple concept. Look here. Suppose we know, actually in kinematics or motion in a plane, we have studied the horizontal projection from the top of a tower. See here, let this be a tower. A body is projected horizontally with a velocity u. It takes a parabolic path and finally it touches the ground. If the horizontal displacement is x, we know x is equal to ut, where t is equal to square root of 2h by g. We have done so many problems based on the topic, and also in previous JEE, there are so many problems exclusively on that particular formula. So, we are quite familiar with that formula, right? Now, x is equal to u square root of 2h by g. See, in this case, on pressing this and releasing, this ball, it is ejected out of the gun with a velocity u from a height 2 meters at what horizontal distance d it strikes. See here, first h is given. In this problem, h is given as 2 meters. And you are supposed to find the horizontal distance, which he has given it as d. In this formula, we need to find out that x which is given as d in your question. So, you can find out x in this case only when u is known. So, how do you get that potential energy of that compressed spring? That is the principle of a gun, isn't it? The potential energy of the compressed spring will be converted into kinetic energy of the bullet coming out of the gun. So, half k x square is equal to half m v square. If you take it as u, half m u square, half and half gets cancelled. So, u is equal to square root of k by m into x. In this problem, what is the value of k given? What is the spring constant? It is given as 100 Newton per meter, that is 100 Newton per meter, and mass is given as 100 grams. If you convert that 0.1 and it is compressed through a distance 0.05, this is 0.05. So, u is equal to, this becomes 10, isn't it? So, here this is 10 root 10 into 0.05. So, this is 0.5 root 10, that is u. Okay, just substitute that value of u here in finding the horizontal distance in this formula. So, x, he has given it as d. So, d is equal to u, that is 0.5 root 10. Square root of 2, h is given as 2 and g is given as 10. Root 10 gets cancelled. It is 0.5, 2 2's are 4 under root, it is 2. It is just 1 meter. So, the answer is 1 meter here. It's a beautiful problem, isn't it? So, just the concepts involved are 2 here. In case of horizontal projection from the top of a tower of height h with a velocity u, horizontal distance at which it strikes the ground is x is equal to u t. T is square root of 2h by g. In this question, the velocity of the bullet is the lost kinetic energy of the compressed spring of the gun will be converted into the kinetic energy of the bullet. So, half kx square is half mu square. So, the concepts behind the problem is that one and this. Okay, go to the next problem. Look here, as shown in the figure, a particle of mass 10 kg is placed at a point A here. When the particle is slightly displaced to the right, on reaching the point B, what is the speed of the particle? It is so simple. See, lost potential energy is equal to gain in kinetic energy or gained Ke. Lost potential energy is mg into h1 minus h2, that is half m v square minus u square. See, look here, m and m gets cancelled, g is given as 10 here, 10, h1 is given as, this is at a height 10 meters and this is at a height 5 meters. So, 10 minus 5, that is equal to half. Final, initially it is at rest, so half into v square. So, from this v square is equal to 10 minus 5 is 5. 10 into 5 into 2. So, if you bring this to the other side. So, v is equal to 10 into 10 under root. This is 10 meter per second. So, the value of x to the nearest integer is 10 meter per second. So, x is equal to 10. So, lost potential energy is equal to gain in kinetic energy of the system. Go to this problem. Two particles of masses 4 grams and 16 grams are moving with equal kinetic energies. Masses are 4 grams and 16 grams. Both of them have the same kinetic energy. Ratio of magnitudes of linear momentum. Quite simple, isn't it? What is the relation between kinetic energy and momentum? So, kinetic energy is equal to p square by 2m. Here both the particles, they mentioned in the problem that both the particles have same kinetic energy. Ke is constant. So, from this relation, p is proportional to square root of m. P proportional to square root of m. P1 by P2 is equal to square root of m1 by m2 implies ratio of their momenta is m1 is 4 grams, m2 is 16 grams, 1 by 4 under square root, it is 1:2. So, here it is as n:2. In place of n, we have 1. So, the answer is 1, right. So, here p is p square proportional to mass. So, p proportional to root m, that is the answer. Okay, go to the next problem. Two solids of masses 1 kg and another body of mass 2 kg are moving with equal linear momentum. Okay, then the ratio of kinetic energies. Again the same model. What is the relation between kinetic energy and momentum now? So, Ke is equal to P square by 2m. As they have the same momentum, Ke is inversely proportional to mass. So, Ke of the first body by Ke of the second body inversely proportional to the mass of the second body by mass of the first body. Mass of the second body is given as 2 kg, mass of the first body is given as 1 kg. The ratio is 2:1. So, in place of A, you have 2. So, the answer is 2 here. So, the numerical value in place of A, you have 2. So, the answer for that problem is 2 here. Okay, both are similar models. Move on to the next problem. It's interesting. A body of mass 0.5 kg travel on a straight line with a velocity 3x square plus 4 meter per second. Net work done by the force during its displacement x is equal to 0 to 2 meters. So, here work done is equal to gain in kinetic energy or integral F ds. The net work done is integral F ds. F is m a, so m a into ds. See, acceleration is dv by dt or dv by ds into ds by dt. Okay, so this is acceleration, right? So, ds by dt is nothing but velocity. Let us try to find out acceleration from this expression here. We can just substitute that acceleration here. So, acceleration is v is equal to 3x square plus 4. So, d by dx of 3x square plus 4 into v. Okay. So, look here. D by dx of 3x square is 6x into v is 3x square plus 4. So, what will be acceleration from this? What is acceleration from this expression? Okay. So, A is equal to 6 3s are 18. 18x cube, 6 4s are 24, it is 24x. So, let us substitute that A here. So, let us substitute work is equal to m, that is 0.5, and acceleration 18x cube plus 24x into ds. ds is taken as x here and the limits are from 0 to 2. So, here 0.5, let us take it outside. 18 x cube integral is x to the power of 4 by 4. X integral is x square by 2 and the limits are 0 to 2. Right? So, here look here. This is equal to 0.5 into 18, upper limit 2 to the power of 4, that is 16 by 4. This is 12, x square is 2 square, that is 4. So, this is 0.5 into 18 4s are 72 plus 4 12s are 48. 72 plus 48 is 120. So, this is W is equal to, see here, 0.5 is half of 120, that is equal to 60 joules. So, work done is equal to 60 joules. So, you do this problem twice. Just follow the video. After that, just have that question and do that problem all by yourself. That's an important, interesting model. Go to the next problem. A particle experiences a variable force, that is 4x I bar plus 3x square j bar in xy plane. Assuming distance in meters, force in newtons, particle moves from the point 1, 2 to 2, 3. So, force is given as 4x I bar plus 3y square j bar, and the particle moves from the point 1, 2 to 2, 3. So, here work done is equal to integral f dx plus integral f dy, and you have to substitute the limits. So, the limits of along x is 1 to 2. The limits along y is 2 to 3. So, here integral 1 to 2 4x dx. So, fx dx and this will be fi dy. 4x dx plus integral 2 to 3 fy is 3y square dy. Okay. So, here work done becomes w is equal to 4 integral x dx is x square by 2. The limits of x are from 1 to 2 plus limits of y are from 2 to 3. Fy is 3y square. So, it is 3 y square integral is y cube by 3. So, here it gets cancelled, integral 2x square plus y cube, you have to substitute the limits properly. So, here it is 2, x square is 4 minus 2, x square if you substitute the lower limit as 1, it is just minus 2 plus substitute the upper limit 3 cube 27, 2 cube 8. So, it is 8 minus 2, 5, 27 minus 8, 27 minus 8, it is 19. So, it is, look here, I think let us do the calculation part once again. There might be a small mistake in the calculation part. So, let's move on to the calculation part. See here, work done will be 4x square by 2 plus 3y cube by 3, and the limits are 1 to 2 for x, 2 to 3 for y. That's it. Okay, 4x square by 2, 3y cube by 3. So, this is 2. So, this is 2, x square is 4 minus 1, right, plus y cube is 327 minus 2 cube is 8. So, here 4 minus 1, 3 2's are 6, 27 minus 9, it is 19, 6 plus 19, it is 25 joules. This is the correct answer. So, here instead of 6, I have taken 5 in the previous, that's it. Okay, it's a simple calculation mistake. Move on to the last problem for today's class. A block of mass 2 kg is attached to one end. Mass of the block is given as 2 kg. Attached to one end of a massless spring, other end is fixed to a wall. Spring mass system moves on frictionless horizontal. Spring has a natural length. Natural length of the spring is given as 2 meters and the spring constant is given as 200 Newton per meter. Block is pushed such that the length of the spring becomes 1 meter. So, here then release the distance, the speed of the block. Once again the question is the system is like this actually. This is a spring, this is a block, the system is on a horizontal smooth surface. It is being compressed and released. So, the lost kinetic, the gain in kinetic energy of the block is lost in the potential energy of the compressed spring. So, lost potential energy is half k into x1 square minus x2 square, that is equal to half m into v square, because initially the block is at rest. So, here half and half gets cancelled. So, v is equal to square root of k by m into x1 square minus x2 square. See here, what is the value of k given? It is 200 and mass is given as 2 kg. x1 square is the actually what is the initial compression produced. Length is 2 meters, final length is 1 meter, so the compression produced is 1. So, initial compression is 1. In the second case, initial length is 2, final length is given as x. So, 2 minus x whole square, that is velocity. So, you are supposed to find velocity of the block when the compression is x, isn't it? So, here this is 100 under root becomes 10, root of 1 minus 2 minus x whole square, under root is taken as half here. So, just look at the option, it is 10 into 1 minus 2 minus x whole square to the power of half. Okay. So, with that I will stop here for today. I will continue with some more problems in the next session. Thank you and bye-bye.